This is 22 Bishopsgate in London. I know it's not Dubai or Medellin, but it's still a beautiful city, and since you're here, you might as well just go and have a look around. 22 Bishopsgate is which is going to be the new tallest skyscraper in the city of London. Second to the Shard, which you can see on the left-hand side, and luckily is one of our company's buildings as well. Before we start, just who I am. I am Diego Padilla Phillips. I joined WSP 3 years ago. I'm originally from Peru, and my involvement in this project was the design management for all the foundations, basements, the transfer systems in the foundations and the concrete core, and now I am gradually inheriting the superstructure as well. So a big responsibility. And here with me is my colleague Carlota. She is one of our super smart people that designed the whole building as well. Let's hope this works. It's a little video. So as we fly from Waterloo Bridge to the City of London, that gap between the Gherkin and the Heron Tower, between the Cheese Crater as well, that is where Bishopsgate is going to be. It's a 62-story building. It's going to be 278 meters. The cost of the project is £600 million, and it's going to host 15,000 people. It's possibly the first in its kind in being a vertical village in the City of London, providing shopping space, amenity spaces, office spaces as well. The interesting thing about this project was that it is going to be built in the site of a previous building, the Pinnacle. So before that, we had 38 Bishopsgate, which was a building that was affected by one of the bombs a few decades ago, a terrorist attack. On that site, the Pinnacle was going to be built. This was before the recession in 2008, 2009, and the building, unfortunately, was only built up to level 7, the core of the building. I say unfortunately because I think, personally, that it was a beautiful, beautiful design. And now it's going to be replaced by another fantastic design, this time much more efficient, much more true and honest to the current economical situation. What were the challenges? Well, the site constraints, as you can see, is in the middle of many, many towers. The City of London has very stringent and demanding planning requirements as well. Program constraints, everyone wants to build the towers as soon as possible. But also, I said, unfortunately, that the Pinnacle wasn't built, but also, unfortunately, it was built, because we were left with 3 stories of basement in the ground that we had to reuse for a completely different building. A foundation built like this, and a building like that. So our challenge was trying to marry the superstructure, which didn't correspond to where the foundations were. So we had existing Pinnacle basement, existing Pinnacle foundations, and pre-existing Pinnacle foundations as well. And of course, we had to always provide a super efficient design, regardless of all the constraints. So I would like to take you through all of the elements of the building, and hopefully we'll get a glimpse of what the challenges were as well, and how we used Bentley software to overcome these. So that is the existing site. I'll talk you through a demolition and enabling works. What you see there is the stump. It was nicknamed the stump, the 7 stories of the previous building, which we had to demolish. At the same time, we had to demolish partially some of the existing basement, levels B1 and levels B2. Now I'll show you what the basement looks without any of the slabs. So that is the level B3, but also we had to demolish part of it, because on the left-hand side is where the core for the previous building would have gone. Now this building is much bigger. The footprint of the core is also much larger, so we had to provide additional foundation capacity on the right-hand side as well. If we spin this around, you'll see what the foundation looks like. So that's what it looks like. All the elements in grey are existing, and all the elements in blue are new. To analyze this interaction, we used RAM concept, and we modeled all of the elements, existing and new, which is very, very complicated geometry. We also exported all the spring reactions for the piles and from the geotechnical analysis, and tried to make them both compatible and try to interpret how the foundation was going to work. So I'll show you what the foundations actually look like. Hopefully it works. Right. So before they build the pinnacle, you can see all of the piles, all of these piles highlighted in blue are undering piles supporting the inside the clay. These were for the previous buildings, 38 Bishopsgate. When they started to construct the pinnacle, they built the new piles in dark blue or purple. Some of these piles are 2.5 meters in diameter and go 50 meters deep into the strongest strata, which is the Thanet Sands. As you can see, there's a concentration of piles on the left-hand side. That is where the core was going to be for the previous building. Our core is slightly different. It's a little bit bigger. The size of our core, which is overlaid there, corresponds actually not to the stability requirements of the building, but the number of lifts required to mobilize 15,000 people up and down, up at 8 in the morning or 9 and down at 6 p.m., but especially at lunchtime. That is the critical time. So how did we manage to provide additional foundation capacity? The idea originally was to create or build 16 new 2.4 meters diameter piles where we required them on the right-hand side. But to do this, we would have required a rig from ground floor, drilling through 3 stories of basement, and then 50 meters into the sand, into the clay, to the sand. And that required temporary works, and the cost was large, and also there were program implications. So we were limited by a specific size of pile for a rig that could fit within the existing basement 3, and that was 900 millimeters in diameter. So instead of having 15 piles of 50 meganewtons capacity each, we ended up having 85 piles. So if someone wants to build a building here in the future, they'll just find a massive lump of concrete there. So let's spin this around. I'll show you what it looks like from the side. So those are the depths, the big piles. And our piles, the 85, they couldn't be as deep as the 51, so they could only go 25 meters into the soil. Because if they were 26 meters or more, they will go into the gravel, will go into the saturated strata, and it will require bentonite to be poured inside the pile to stop the water from coming in. So there were so many factors limiting the depth and the position of these piles. Let's move in a bit higher into the building. As I mentioned earlier, the building footprint corresponds to a different design, and the foundations didn't match this. So we had to transfer all of the loads somewhere. And where else? Where would be better than the basement? Which is a shame, because no one's going to ever see these big transfer structures, because they're all buried. What happened here was we had 3 big columns, 60 stories on the left-hand side, and we had already existing mini piles. I say mini piles, but they are 600 millimeters diameter, but compared to the scale of the rest of the project, they are mini piles. So we couldn't really build any additional, we couldn't really provide any additional foundation capacity on this side. All we could do is build a raft to try to spread the loads into existing foundations. But also, since the loads for these 3 columns were so large, the new raft was failing in punching shear through them. So we had to spread the loads using these A-frames. They've just installed these A-frames. I haven't got a photo with me, but they look really, really, really great. On the south side of the building, because of the waste management strategy, we couldn't really have that column that you see there going all the way down to the foundation. So we required the transfer structures. This is a 14 meters long beam, is 3.5 meters deep, and it weighs 97 tons. I have a photo of what it looked like when it was being installed. They had to close many roads in the city of London at 3 in the morning, I think, to install it. You can see the scale compared to one of the operators on the side. It looks like a house with little windows on the side. Of course, why would you have a vertical column if you can have an inclined one? Are there any architects in the room? Because I always make a joke about architects. So we couldn't have this column vertical because of the waste management strategy at the base. So we had to incline it, crank it at ground floor. And because of the push and pull forces created by the inclination of an element, you know, when we are inclining, I was advised not to leave this. If you're inclined, you try to move forward. So you need something to restrain you back. And that's what these McAlloy bars are doing, restraining the column and resisting the horizontal forces back into the core. And the force in this column is 60 stories, so it's like 60 or 70 meganewtons, which is gigantic. Let's move on to concrete, which is what I like doing. Of course, also we had columns at a different position in superstructure, and we didn't have the corresponding foundations in the substructure. So we had to transfer these loads, gigantic loads, using concrete walls all the way around. For the analysis and the modeling of the basements, we used RAM concept as well. And as you saw previously, we had 3 levels of basement, 3 slabs, B2, B1, and the ground floor, and we had to build around them and through them, and trying to keep as much as possible of the existing foundations without demolishing and without using many temporary works. So this is a small image of what the analysis models look for software. Lots of openings, lots of penetrations for all the lifts and etc. That is what it looks like currently. We are on level 7 on one side and level 1 on the north side. And the reason why the core is going at 2 different speeds is because on the left-hand side, we had an existing foundation, so we were able to dig up to the basement 3 and start building the core from basement 3 and up, as you would expect a normal building to happen. But on the right-hand side, which is the south, we didn't. That's where we had to install the piles. And to save time building the piles, we started building the core at the same time as we built the piles. So below that, there's a transfer structure, and there are no columns. So there are no foundations, but you are already building above ground floor. And we're going to build up to 25 stories before we connect the foundations with the rest of the tower. And that is why this is going higher and first. In an ideal world, a tower would go like this. But in London, sometimes time constraints and money constraints are so demanding that you can't really build the building traditionally, although this is very optimistic. Hopefully one day I'll get to build a tower in the traditional way. But this shape is the result of a series of iterations. This is the final product. To get to this point, we had to iterate up to 70 times, and that's when we used Bentley, the integrated structural modeling. If I click on the next one, you look on the left-hand side, that is how the shape of the building evolved. I've only selected, I think, 10 or 12. But there were 70. So each of these iterations takes 1 or 2 engineers for a week to remodel. And we used Revit integrated with Bentley, with RAM structural systems, so that we could produce drawings at the same time as we modeled the building seamlessly. So by doing this, we saved, instead of doing this in 70 weeks, we did it in 43 weeks. So we saved nearly 40% of time in engineering and modeling time. So what does a typical floor look like? As you can see, the size of the core, it's very large below level 25. It's a typical 130 millimeters lightweight concrete slab. That is what the steel frame looks like. And the steel floor, the steel frame was analyzed using RAM structural systems. At some point during the design of the project, it was requested to change all the elements to FabSec. So we integrated RAM with FabSec to export all the sections and design them in FabSec, design all the openings and all the stiffness very, very quickly and very easily. And also our client sometimes is quite demanding, so they require constant changes, and that just works really, really seamlessly. As part of any standard office building, we carry out a floor vibration plot. You can see the areas where the vibration is maximized. And we also carried out a fire assessment. The way we analyze fire, the way we analyze this problem is by replicating the effects of fire and seeing which elements start failing first, and that way we can determine which beams to fire protect for what length of time. That way, instead of just specifying that all of the beams have to be protected for 90 minutes, some don't need any fire protection, some need 30 minutes, some need 90 minutes, and that way we save a lot of money in fire protection. And finally, in the floor, for a typical floor, robustness and disproportionate collapse. This is a very, very important part of the design of every building. You need to provide an alternative way of motor failure, alternative redundancy. So in this case, we have a tie around, all of the elements are tied around the building so that in case of one of the columns failing, the catenary action, if the column fails, the catenary action between the other two makes sure that the building stands up with large deformations, yes, but it remains standing up in the case of one of the columns failing. Of course, lateral stability, a very important part of the design of a tower. In this case, the lateral stability system is provided the resistance is provided in one direction by the size of the core. This is in this direction. And in the opposite direction, because of the slenderness of the core, we required an outrigger system. 2 levels of outriggers with outrigger belts. They were modeled using a combination, of course, of different software, including RAM structural systems as well. Just to get to the end of the presentation, we had transfers in the basement, but also we couldn't really have straight vertical columns in the superstructure, so we required some elements to be transferred. There they are. So you can see some of these columns, inclined columns as well. So 50 stories above, and then they incline. And to resist this very large lateral forces generated by the inclination, we had to create and analyze and design a horizontal transfer system. We saw that in the basement, the inclined column was tied back to the core. But here we couldn't really do that, because if we used high-strength bars to tie back into the core, they will interfere with the surfaces running through all of these openings. So we had to make the floor plate, behave horizontally to take all these forces. And it wasn't enough to take the forces back into the concrete slab. We had to engage the steelwork as well. The top elements resist the tension forces being pulled, and the bottom elements resist the compression forces, which in the case of steel is more onerous. On the right-hand side, that part of the basement had to remain in operation during construction, so the 3 columns at the top couldn't really go down to the foundations, and we had to model this beautiful, the Rhino, it's called the Rhino truss, to transfer all the loads from the top of the building to the truss, into two new columns, into new concrete elements, and into new piles at the base. So 22 Bishopsgate has been a very interesting project. Using the use of Bentley systems allowed us to save 40% of the time, design time. We used the RAM and Revit integration, RAM FabSec integration, and all of this with the Eurocode's compliance, which facilitated the process and made it quite much more simpler. Some of the achievements of this project was we managed to reuse 100% of the existing foundations. We added some extra capacity. We reused 50% of the existing basement. We were successful in providing an efficient design. We provided 30% more floor space in 22 Bishopsgate than the previous scheme, which I think is a really, really good bonus. Hopefully when it's finished and you get a chance to come back to London, it will have a nice restaurant at the top and also the tallest observatory public space gallery in the city. Thank you very much for you.